my gosh. Where are we? Where are we? And who are we? Here's Fuji. Here's the astrophysics book that we know and love. Here's the authors. Here's Suji Mama. Here's Baji. And Fuji is over here as well. But we are in a different room in the house. This is quite extraordinary. Generally, we're downstairs in the living room kitchen area. And that's where we do our lives. But right now, we have some work going on in the house. We have housekeeping and cleaning happening. And so we have to be upstairs, and the kitty cats have been trying to get into. So we are good. They were downstairs to get their food, water, and bathroom and all of that stuff. But they are a little bit affected by the cleaning happening, and Fuji wants to go investigate and supervise some of the cleaning. But because of all the chemicals and the doors opening and closing, we are safely upstairs. So here is Baji. And I promised you guys that I will finish up the quasars section of the live. We were trying to talk about active galaxies for a few lives, but then we got some excellent questions, and I believe I never really finished the quasar section. So I want to do that today at this time, and then I'll let the live stream get posted. And if you're seeing this as a video later on, welcome, welcome. Thank you so much for being here. Welcome to the live. Here we are. Here we are. Here is Baji. He is a little bit sleepy right now because he has been up most of the afternoon with all the cleaning happening. Fuji! Fuji! Fuji Baba is, he is pretty much friends with the housekeeping, and so he wants to go say hi, and he's very social. Fuji! Fuji Baba, Mama's here, baby. Hi, Ram Candy. Hello. How's everybody doing? I'm going to share the live soon here, but if you guys can share the live, that would be really excellent as well. Thank you for liking the live. Thank you for liking. Hi, Ram Candy. Hi, Kitty Monster. Hi, Jay. Fuji. Fuji. Fuji Baba is Flowey. Shona Fuji. Hi, Ram Candy. Hi, Kitty Monster. Jay says, loaf, 8.9 out of 10 loaf. Hi, Helena. Helena Santos, our brow says, hola. Thank you, Kitty Monster. Kitty Monster says, your cat is super cute. Thank you so much. That's very kind of you. Thank you for all these comments. Love it. I'm going to read all of your comments and your username out loud. Deep BX says, hi, where are you from? We're in Boston, Massachusetts. Matthias says, hola, hola, Matthias. Cassandra says, hi, hi, Cassandra. Kevin says, cute cat. Jess says, oi, 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 cat. Hyrule Ben says, or Hyrule Ben, Brambat, says, heart emoji, thank you. Hi, Ram Candy. Hi, Charity. Hi, Hyrule Ben. Hi, Britton. Hi, Maxie. Thank you, Maxie. Says, he's so handsome. Britton says, the cat is cute. Thank you. Sawyer says, if you're not going to eat that loaf of bread. Charity says, is it nighttime? Yeah, the sun sets very early. You know, it's already past 5 p.m. here in Boston, so it's already very dark. Do you have any other cats? Oh, yes. Do you want to add me on Fortnite? Oh, thank you. Thank you for considering that. Here is Suji. Hi, Fuji. Hi, Fuji Baba. Do you want to come up and say hi? Hi, Fuji. Come up and say hi. Hi, say hi to Mama. Hi, say hi to Mama. Hi, say hi to Mama. Fuji Baba, Mama loves you. Let housekeeping get finished, okay? They will tell us when it's done. It smells so good here. It smells so good. It smells so very good. Mama's getting the house cleaned now, bacha. Mama's getting the house cleaned because Why? Because there was so much dust, so much dirt, and now we will have clean house. Quite literally, clean house. Clean, clean. Come, baby. Oh, Fuji needs love. Oh, I'm so sorry, Fuji. So Fuji's the security head of the house, and he just feels like he needs to control the narrative of exactly how this housekeeping is happening. But there's so many chemicals. We don't want to be in the chemicals. We don't. That's why we're here in this new place. We're here where we sleep. We're here in the bedroom where we sleep. Maxie says, what are their names? Their names are Fuji, Suji, and Baji. Sawyer says, another loaf of bread. This is my Fortnite account name. Thank you, Charity, for sharing. Royal says, Aap kahan se ho? I'm from India originally, but I've been living in the US for, I don't know, half my life at this point. Charity says, that's my favorite, or that's my Fortnite account. Okay. Aap kahan se ho? We're in Boston, but I'm from India. Do you have Roblox? I do not. You can share what you know about Roblox. I think we do have some friends of the channel who really enjoy Roblox, actually. The cat on the bed reminds me of Chill Guy. Yeah. Yes. Sawyer, thank you for the comment. Oh, thank you. This this kitty cat, Baji, is very chill indeed. He did not get a lot of naps today. Look at where we are. We're up here in the bedroom. Doro, the mod, is here. Whoa, I actually made it to live. Thank you. Thank you for joining, Doro. Sawyer says, welcome is my Roblox account and my password. Oh gosh, yeah, maybe don't share your password on the YouTube live. What kind of books do you read? So right now I'm reading a lot of astronomy. So here, this book, we will actually share something from this book in just a second. Here, we're gonna talk about quasars and finish up that section. But I really love murder mystery books, actually. So I've read many murder mysteries. That's my favorite. That's my favorite genre, pretty much. For fiction. Always thought the top floor was a myth. Oh, yeah. This is it. This is an attic, sort of a finished attic. This is the bedroom. This is where the kitty cats and me relax and sleep and whatnot. We are up here today because there is housekeeping and cleaning happening downstairs. So look what I sent you. I'm trying to make YouTubers happy. I'm picking 10 people. You're my 5th. Okay. This is where the 19-hour breaks happen. I see. Aw, yes. Yeah, yep, this is where it happens. Indeed. Indeed. Once we come up here, it's like Narnia. We don't know time anymore. Once we come upstairs, it's like entering the Chronicles of Narnia, and we don't see. Look at all those shoes. Shoes? Which shoes? You haven't seen my shoes yet. Always thought the top floor was a myth. So Dora's used to seeing us upstairs, or not upstairs, downstairs in the living and kitchen where we go live normally. I'm just sitting on the floor. Flowey! Fuji baby! Fuji really, oh no, that's my bathroom stuff, like all kinds of, I don't know, those are like bathroomy type of things. What's on there? Let's see. There is some lotion, there is sunscreen, hair, don't show it. No need to know. Yeah, exactly. So it's over there is the bathroom. So that's probably what you saw. I have a whole closet for the shoes, and those are downstairs. So I don't think there's any shoes up here. I'm trying to make YouTubers happy. I saw that comment, whatever that means. Thank you for making us happy. Don't show it. Yes. Oh my God. Oh my God. Yes, exactly. So we are showing Baji today. Baji is the most chill one right now. Fuji is over there investigating the chair. It smells nice in here. We're getting it cleaned. We're getting the place cleaned. Oh, thank you for liking the live. Thank you for liking the live. Can we get 10 likes? Baji wants 10 likes. Baji wants 10 likes. But yeah, I don't think I'm going to go towards the bathroom. The bathroom is where bathroom things are. And we do come up here to cross into Narnia sometimes. And and Baji will get wild once you start your lessons. Thank you, Sawyer. Thank you for liking. Oh my gosh, thank you for liking the live. Maybe we'll get 20 likes. Can we get 20 likes? I start asking for the likes and then it sort of does happen. So I am happy that everybody is so supportive. Thank you so much for being here. Thank you so much as usual. Welcome to the live. Welcome to this video. If you're seeing this later on as a video, we're gonna talk about some quasars. So pretty much the lives at night have been super busy. 12, yes. Oh, hello. Hello, everybody. Thank you for being here. The lives at night have been really busy. I've been getting a lot of really good questions. So that has taken up time to kind of things to be covered. And then this weekend, this weekend and next weekend, it's going to be a little bit busy. I've got some things going on, some family visits and whatnot. So that's why I'm posting a lot of the shorter clips and videos, outside of the lives as well. So hopefully you can see that and watch it and enjoy it and leave me a comment still. It can be sort of like the live chat, but my videos sort of instead of that. So hopefully you catch a lot of that and enjoy. And thank you so much in advance for all the support and comments. My favorite YouTuber of 100. Oh, thank you, Sawyer. Hello, the live chat. No, nothing beats what happens there. Very true. Very true. So I will be back before you know it to the nighttime live. Probably in a couple days, I'll be back again for the nighttime live. So this is the live I'm doing right now, but then there is usually a nighttime live. Maybe made it through. I got a message on my phone. My main men, Reese and James. Yeah, so I don't know if you saw the live maybe a couple nights ago. They were both there and we got a lot of astronomy and cosmology questions. It was a really good discussion and we had a lot of fun. So yeah, everybody, if you're new on the live, we go live at night as well. That happens almost every night. And it's this late night live. We cover physics topics, cosmology, astronomy, all that. And lately, we've been getting really, really good questions. And that has been really fun to cover, and people have been engaged, and that was really nice. And this is so we also go live, like sort of like this in the afternoons or evenings, where I show the kitty cats because there are a handful of people who do like to see the cats as well and get an update on the cats. So here they are. I've been very busy and sick. Oh gosh. Well, I hope you feel better, and good thing that you're busy. That's good. Good to be busy, but not good to be sick. So hopefully you take care. But will there be cats in the night one? Yes. So the cats appear in the night one as well, but the night one is generally me on camera and showing the cats as well now and then. But yes, they appear in pretty much all videos, any videos and all videos. They appear where they want to appear. The cats are the ones who are running this house and this show. So thank you for liking the live. Thank you so much, everybody. Thank you so much for your support. People are engaged to Google so they can know what you are talking about. I went to McDonald's. Oh, nice. Yay. Thank you so much for being here. So here we are. Thank you so much for your comments. Keep them coming. Keep your live chat messages coming. I'll keep reading them. And let me get started on the topic for today. So we have been kind of covering this topic for a few lives, but we have been interrupted, but in a good way. We have been getting a lot of questions, and we've been covering those questions instead. So if you've been seeing the lives and thinking like, oh my gosh, when will this topic be covered fully? Here it is. Hopefully I actually get through it and finish it properly today. So we're going to be talking about active galaxies and an example of that, which is quasars. So we have spent quite a bit of time talking about sort of what we consider more normal galaxies, like, and really normal as in where we classify them normally as either spiral galaxies or elliptical galaxies or irregular galaxies. And we have actually covered these types of galaxies already. So that's the Hubble classification. Hubble, as you know, amazing astronomer from about 100 years ago who really opened up our minds and our eyes quite literally to the rest of the universe in a way, in an astronomy sense of the word, because, you know, the universe as a whole is, of course, very big. It evolved a lot from the Big Bang to where we are now. But as far as other galaxies go, that was something that, and even cosmology as a field is something that has really developed a lot in the last 100 or so years, because we really didn't have a sense of how big everything really is, how big the universe really is, how many other galaxies really there are, and things like that. Doing observations in astronomy is what opened our minds and eyes to the sheer sort of hugeness and enormity of the universe, and the fact that there are many, many more galaxies. Not only some more galaxies out there that are not even our own galaxy, but many, many, many more galaxies. And as more and more were discovered, Hubble found a way to classify them according to what we call morphology. So morphological classification, or pretty much simply put, it's based on shape. So the shape can be either a spiral, like our own galaxy, the Milky Way, or it can be an elliptical, such as literally the shape of an ellipse. It's a bright blob, usually this type of galaxy in the shape of an ellipse, and the ellipticity could be something that's kind of different. And based on the ellipticity, we can further subclassify them, subclass, not just subclass them. And then we also have galaxies that are sort of, they don't really have any good shape, so we call them irregular galaxies. And in that context, we actually also talked about how galaxies will sometimes cannibalize other galaxies and pretty much merge with another whole galaxy. And we considered those as well, some galaxy mergers. And we talked about that. And I think that was something that people kind of resonated with, and some people asked about Star Wars and some other science fiction type of questions. So hopefully, if that's an interest, we can find some overlap with that here as well. And I'm quickly kind of summarizing for you because we do have a whole another discussion today. But yeah, we talked about galaxy mergers as well in the last few lives, and also about the fact that the Milky Way galaxy, our own galaxy, will merge with Andromeda, and this merger will pretty much happen over the course of the next 6 billion years, where there will be what we call a close passage within the next 3 billion years, or 3 giga years. So in astronomy cosmology, these types of fields, the timelines are kind of much different from what we might be used to as humans. We consider on the scale of billions of years, versus just decades and things like that. So let me read some of these comments again, and then we will keep on going with today's topic, which is active galaxies. Active galaxies are sort of a topic of their own because, as you know, we talked about the just normal, if you will, galaxies, which are the spirals, the ellipticals, and the irregular galaxies based on shape. Now, active galaxies basically will have an active galactic nucleus. So the way in which active galaxies are different is that they have a lot of the stuff that we associated with galaxy stars and things like that, but they have a major share of the luminosity of the galaxy coming from an active galactic nucleus. So this activity, is associated with something like a supermassive black hole. We will find out more. But as you know, even we in the Milky Way galaxy have a supermassive black hole at the center. We talked about that too over the course of a few lives. It is called Sagittarius A star, and it's considered with it's a part of the Sagittarius system at the galactic center. So we talked about that at length as well. But we are not considered an active galaxy because most of our luminosity in the galaxy don't just come from that particular galactic center. So if your galactic center is so active, and I guess other parts of the galaxy are not as bright, where the galactic center or the active galactic nucleus pretty much competes or even beats the luminosity of everything else put together, then those galaxies are called active galaxies, as in the main sort of feature of them is the activity in in their active galactic nucleus. And so that's what the classification or that definition means. So here we are, and yes, the cat moves. Let me see your comments. Okay. Is Kitty here? Kitty Monster. So Dora says we need James in here. I'm the Spiral Galaxy. I'm leaving my okay. Is your cat's name Kitty? No, this kitty cat is called Baji. And okay. Interesting chat as usual. Okay, so thank you once again for being here. We will keep on going with this topic of active galaxies. Active galaxies have many distinctive attributes that distinguish them from the normal galaxies discussed in the previous chapter. As briefly mentioned so this, by the way, is chapter 21 of this book, if you're interested. And we kind of mentioned them, the authors mentioned them in an earlier chapter, but we will keep on going here for the moment. Active galaxies produce large amounts of non-stellar emission. So as I was kind of saying just a bit ago, this non-stellar emission and the luminosity coming from sort of that active galactic nucleus versus the stellar emission. Because see, most galaxies, like our galaxy, has a bunch of stars. It actually has around 200 billion stars, and most of the luminosity is coming from that stellar luminosity. So that's considered more of a normal galaxy. But if your galactic center's activity is the main luminosity, or its luminosity is so huge, it pretty much rivals the luminosity of everything else put together, then you would classify as an active galaxy. Okay, so some of it is non-thermal in origin, the non-stellar emission arising from energetic and violent processes. So we're talking about active galaxies again here. Non-thermal could be part of the emission. It could be from energetic and violent processes. Active galaxies produce more radio and X-ray emission than you'd expect if all their light came from the photospheres of stars. Active galaxies have much of their light concentrated in a small central region known as the active galactic nucleus, or AGN. Light from the AGNs is variable on short timescales at virtually all wavelengths. The timescale for significant variability is dependent on both luminosity and wavelength, with the most rapid variability seen at shorter wavelengths in lower luminosity AGNs. In low luminosity AGNs, X-ray emission can vary on timescale of minutes. So remember how we talked about gamma ray bursts, and gamma ray bursts, remember, they were classified as two types: short gamma ray bursts and long gamma ray bursts. And depending on how long really they are, the short gamma ray bursts could be as short as less than 2 seconds long. So we kind of saw things like gamma ray bursts, which are basically transient events, as in when they're basically associated with cataclysmic events that release a large amount of energy and luminosity, where the luminosity is so high that it can rival the luminosity of an entire galaxy when the gamma ray burst is actively emitting. And again, just a quick reminder, gamma ray bursts were associated with either hypernovae or really, really big supernovae if they were long gamma ray bursts, and mergers of neutron stars and black holes, or neutron star, or neutron star black hole, or black hole mergers, which were the short gamma ray bursts. And these were some really extreme examples of particle accelerator type of events and environments that lead to these transient sort of bursts of energy coming out. And while they're going off, once again, they are emitting more luminosity than an entire galaxy might. So this AGN, the has variable timescales. So consider this to be all very variable. Active galactic nucleus is not going to be some extremely slow, steady type of thing. So in the low luminosity AGNs, X-ray emission can vary on timescales of minutes. So where the gamma ray bursts could have been timescales of seconds to minutes, or where even longer, this is more in the timescale of the minutes. Okay. Some active galactic nuclei have jets that are detectable at X-ray, visible, and radio wavelengths. So once again, this jet type of behavior, basically it's a very active site, as the name suggests. It's not just a slow, steady kind of process. Like, our sun is more or less slowly and steadily burning as a star, and it is converting hydrogen to helium. That's the main process within it, and it's a pretty slow, consistent type of thing that's happening for actually billions of years. The sun is 4.6 billion years old. So that's sort of a much more of a slow, steady, it's a star, it's a process happening, and the sun is an object. Okay, so in astronomy, an object like the sun, it's burning, it's a star, it has a nuclear reactor within it, and it's existing on the scale of billions of years. Whereas something else like a gamma ray burst is a transient event. It's not really considered an object because the object that it was probably a star or a neutron star binary or something like that. And then really the event has to do with something else happening, such as a supernova or a hypernova or a merger. And that particular event is what causes this transient event of the gamma ray bursts. So similar-ish type of thing happening here with the AGNs, where they're objects, but there's a ton of variability in terms of the what's going on. So some active galactic nuclei have jets that are detectable at X-ray, visible, and radio wavelengths. The jets contain ionized gas flowing outward at relativistic speeds. The ultraviolet, visible, and infrared spectra of AGNs are dominated by strong emission lines. So remember, also, I moved my book and startled Baji. Sorry, Baji. You're okay. You can take a little nap and dream about AGNs. So what we mentioned also when we talked about our supermassive black hole at the center of our own galaxy, you will see a lot of sort of, what's the word? You will see a lot of parallels with that here, even though our galaxy is not considered an active galaxy because we have luminosity coming from the stars and it's not as rivaled by our galactic center. But a lot of the things we said about why our galactic center is so bright in radio and also X-ray is because of the falling material into our own supermassive black hole. So the supermassive black hole itself is a compact and dark object, but the reason for it being so supermassive is actually because it has continued to eat a lot of material over the years. And really all that material that's falling into the supermassive black hole, feeding it because of its extreme gravitation, that falling material actually is the one that's emitting a lot of energy. So those materials are falling in and can have relativistic speeds, and that could lead to synchrotron radiation, or it could be just gas that's becoming ionized and stripped and just producing a lot of energy because of that in these other wavelengths like X-ray and radio. So those types of things, the falling material, the accreting material is why the surroundings of the supermassive black hole is so bright. It's because of what it does to the other things that are sort of around it. And the same thing happens with active galactic nuclei. So I wanted to mention that and remind you that when we talk about the black hole at our galactic center, we've done that quite a few times. It'll probably come up again in the chat sometime. You will see a lot of the same things pretty much, but now we're talking about it in the context of the active galaxies. Okay? So here we are, and let's see, the accumulated, actually, guys, give me 1 second. I need to send one message. I see the chat is very busy, everybody hanging out and speaking with each other. Very nice. Continue to catch up, and yeah. Actually, here, you can also look at this, Actually, give me 1 second. I'm going to put this over here. Baji has moved anyway. Hang out with Baji for 1 second. I'll be right back. Okay, everybody, we're back. We can go downstairs again. What? What is happening? Okay, we can go downstairs. Oh my God. And I have to get a delivery, but we are in the clear for the downstairs, guys. Oh my gosh. Hello, Baji. Isn't it so clean in here? Yep. Fuji was extremely annoyed with me for not letting him downstairs. Oh God. Door closed and locked. Goodness. Okay, everybody. Kid's gonna get this whole chat. Okay, Fuji Baba, give me 1 second. I need to fix their snacks because they're extremely mad at me. They're extremely mad at me for making them stay upstairs for like a little bit. Okay. Where is your snack? Right here. See, you can look at this. I have to make there. Oh. Okay. Okay. All right. Ah! Here you go. Where is Sachi? Suji, Mama. Sachi. Okay, guys, hang on for just a second. And can we get more likes, please? Could we get 25 likes? Come, Sachi. It's okay. Come, Sachi. You can get snacks too. Come, Sachi. Here you go. Here you go. Here you go. Okay. All right, I need to fix their water and then I need to go get my grocery delivery. I will be back. Hang tight. Just hang tight. Need to get my grocery delivery. Hello? Okay, what's up? Sorry, I forgot this. Oh yeah, I did. Thank you. Thanks so much. Yeah. Sorry, closing and opening the door is like a whole thing here. It's a whole thing. Okay, now I have to go count the cats. 1, where's 2 and 3? Okay, I see all the kids. 1, 2, and 3. It's just when people come and go into the house, it's like kind of a disaster. I have to like make sure kitty cats are safe and good, well taken care of and inside, and that nothing is amiss. Okay, we're back to our regular environment where we do the lives. The cleaning was happening downstairs is why we had to do we started the live upstairs, but we're back down now. We're back down and everyone got a snack. So we're good. We're good and we got snacks. And now, one more thing, 2 more things. Mama has to go get a grocery delivery from downstairs. You're all gonna be good boys and girls here. Y'all can hang out with the kitties and I'll be right back. And then I'm gonna fix their water. And then we will continue our lesson of active galactic nuclei. Did I not bring my... Yes, I did. Okay. up here. Could you stay inside, please? Hi, Fuji. Please stay in. 1, 2, and 3. Oh my gosh. Alright. Hello. Hi, Fuji. Door. Close. 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 Lock. Lock. Please. 1, 2, and 3. Okay. Oh shit. Did the phone fall? I'm so sorry, everybody. We're here. The phone has fallen, but we're back. We're back. We're back for the most part. Right, we're right here. We're right here. Apparently, the phone had fallen onto the ottoman. So it's all good. I had to get some time-sensitive groceries from the from the stairs. I don't even grab everything at once because it's too much. I just grab the stuff that is perishable and goes bad because I can't be doing so much work all at once. And I really wanted to do the active galactic nuclei, but unfortunately life is happening as well. How is everybody doing? Tostitos, my goodness. Goodness gracious me. Pork hot stickers. Goodness gracious me. Holy crap. Holy crap, this is a lot of bread. It's a lot of bread, man. It's a lot of freaking bread. Holy crap. Wow, okay. Wow, I've never seen such good bread happen before. So this bread and this stuff is actually being sent to me by my dad. And yeah, oh wow. Oh wow. Oh wow, these bags are ready. Wow. Housekeeping has done a really good job. I'm amazed. I'm completely bowled over. But also my dad, ahead of the visit, has sent an amazing, enormous amount of food. I think he was worried that I would be starving everybody, so he sent food. Goodness gracious. Hi, Baji. Do you see what Grandpa has done? It's a lot. I'm not even going to bring everything in. It's too much for me to do. Okay. Okay. I only eat McDonald's. Laundry can't buy groceries. She orders all of her groceries. I mean, I kind of hate going to the grocery store, to be honest. I really don't like it. But these groceries are actually from my dad. He has sent them because he thinks that I have no food for my guests. And no screens, no space decors, no telescope. There is a cat though. So sorry for the interruptions. That was housekeeping and groceries, and now I'm back. And the grocery is from my father. He decided that I have nothing, and he very kindly has sent me food. She only enjoys American. I don't enjoy American football, actually, like at all. Yep, she's fake. Okay. Because I don't, even I had glow in dark stars. Oh, because I don't have my space decoration. Got it. Oh, I see. The space decoration would make me real. Got it. We could talk about real and imaginary numbers. Indeed, we could. We could. So, you can look at my sync now and Baji while we discuss the next parts. So, active galactic nuclei is something of interest here when we talk about the active galaxies. So, and even though other galaxies may have a supermassive black hole at their center, we wouldn't call them an active galaxy if the galactic center part of the luminosity did not outshine pretty much the rest of the galaxy. That's kind of what's going on here with the definitions. So, yeah, okay. The accumulated evidence indicates that the activity in galactic nuclei results from the accretion of matter onto supermassive black holes. And in fact, that is exactly what we talked about with happening with our own galactic center. But it is even more relevant in this case because the luminosity, again, I keep repeating, but it's to be noted that active galaxies pretty much have most of their luminosity coming from this type of stuff where the material is being accreted onto a supermassive black hole. And that material that's falling in is what is causing the luminosity or contributing to most of the luminosity in the galaxies. So small, okay. Hello, SMOL. Can I get a shout out? Thank you for coming to the live. Thank you so much. It's time for pizza, says to shout out their friend. Okay, well, thank you. So that's true. I do live off of protein shakes sometimes. Okay. So now, keep on going here. A supermassive black hole is a necessary but insufficient condition for activity in galaxies. So when we say active galaxies, we don't just mean that there has to be a supermassive black hole, like we have one too. To be classified as an active galaxy, the central black hole must be accreting gas sufficiently rapidly to have a luminosity high enough to compete with or outshine the stars in the host galaxy. So that's really the main thing. In astronomy, remember, luminosity is very important. How we measure luminosity, how much luminosity. Like our own galaxy has about a luminosity, a total luminosity of around 23 billion solar luminosities. So we like to think in terms of our own sun, in many cases, especially when considering stars and galaxies. And the sun has a luminosity of, say, 1 solar luminosity. Well, when you take 23 billion such solar luminosities, you would get sort of the total luminosity of our own galaxy. We don't classify as an active galaxy because the supermassive black hole at the center of our own galaxy, or the galactic center's luminosity is not outshining all the rest of the luminosity in the galaxy. But there are some galaxies where that happens, and those would be classified as the active galaxies. And there are a few different types of active galaxies. Now remember that luminosity or signals of things can be observed in different wavelengths of light. Actually, in multi-messenger astronomy, we have spoken about how we can use different types of particles too to do astronomy. It could be neutrinos, it could be cosmic rays, it could be gravitational waves, it could be of course, light of different wavelengths. I feel like I'm missing something. Am I missing a type of particle? Neutrinos, cosmic rays, gravitational waves, and light of different wavelengths is what comes to mind at this exact moment. But it is to be understood that just using light of different wavelength itself was it's still a little bit novel. It's not that novel, it's not that new, but keep in mind that, we see things in the visible light spectrum, but light exists in other wavelengths too. So you have to keep in mind that some part of a certain galaxy or even our own galaxy could be bright in radio waves, but not as bright in maybe the visible wavelengths. In fact, that is the case with our own galactic center. So we can identify three major classes of active galaxies. These are Seyfert galaxies, quasars, and radio galaxies. Seyfert galaxies and quasars are actually quite similar to each other. Seyfert galaxies can be thought of as a low luminosity. So this is pretty low luminosity. Relatively nearby quasars, radio galaxies are different in that their nuclear emission often is not prominent in wavelengths other than radio. We consider each of these three main classes below. Sorry, no, I'm here. Cats are always hungry. Okay, so all right. Okay. Let's see. Well, I can change my mind, or it's my channel. In case you didn't know. All right. Okay. We will keep going. So, today is a lot happening. Too much going on today. As in my life, not this chat. This chat is as usual, as per usual. But actually, the chat has been a lot better at night. I don't know what I did, but something I did has changed the audience in my night lives, and I get a lot more like actual physics and astronomy questions rather than whatever this is. But this is indeed needed because I need to like get this material done, and then I have like actual life happening. So therefore, I will probably not be live again tonight. So if you're seeing this, I will miss you so much, and I will be back live in a couple nights. I need a break anyway. And please do continue to enjoy the videos that come out and the lives, and go back and watch any of the previous live streams. I wish that I could figure out a way to edit some of the previous live streams and make the content parts more prominent, because I know the lives can be a little random. But, oh God, their cat genie has started, I think, which is also something that's happening apparently right now. I'm on the hunt again, actual life. I can relate. Yes, I have some actual life stuff happening for some time. I had a life once, then the cops ruined it. Well, I think that when there's a trolling happening, sort of like, if it's like a once or twice kind of offender type of thing, then I don't really time them out. But then some people have been kind of being like that's all they do type of thing, and for several days now. So that's why I timed out a few people here that I don't want to deal with. Oh, yeah. Baji has started the cat genie. Great. So there's that happening. Seifert, we will go back to the discussion here. Radio galaxies are different in that their nuclear emission often is not prominent in wavelengths other than radio. And we consider each of these three main classes below. So Seifert galaxies, yeah, the cat genie is another automatic cat litter box, and usually I have it in a manual mode so that they can't turn it on, because the way the cycle runs is a little bit sort of, it gets interrupted too much by the kitty cats. But because I was getting cleaning done, its mode changed and now it's running. So just yeah. So anyway, Seifert galaxies, whose unusual properties were first identified by Carl Seifert in the 1940s, are spiral galaxies with luminous variable nuclei that have strong emission lines in their spectra. So Seifert galaxies have nuclei with luminosity of around 10 to the 8 solar luminosities to 10 to the 12 solar luminosities. So quite a bit of solar, so it's like 10 to the 8, like 100 million suns, or something like a billion-ish suns, if I'm not, unless I'm counting that wrong. Well, actually, let's see. I am counting that wrong. 10 to the 8 is, yeah, no, it's more like 1,000 billion. So anywhere between 10 to the 8 solar luminosities and 10 to the 12 solar luminosities is what we have for these nuclei. There are over 10,000 Seifert galaxies that are known, and it's estimated that about 5% of bright spiral galaxies are actually these Seifert galaxies, but this fraction might be as high as 40% if very low luminosity Seifert-like objects are included in the census. The spiral galaxy NGC 3516 is a relatively nearby Seifert galaxy. I'll show you the picture for this. And these galaxies are two main subclasses depending on the properties of the emission lines in their spectra. The spectrum of a Seifert 1 galaxy is right here. Look at that. Look at that. This is the Seifert 1 and Seifert 2 galaxy spectrums with the wavelength given in angstroms here. And the emission lines from forbidden transitions are relatively narrow with Doppler widths of around 300 kilometers per second. And by contrast, the emission lines from permitted transitions, such as the hydrogen alpha line, have two components. One component of a Seifert 1 permitted line is narrow, but the other is very broad, with a Doppler width of around 5,000 kilometers per second. The broad and narrow emission lines arise in two different regions of the AGN. The broad line region contains relatively dense gas, in which the forbidden lines are collisionally suppressed. The width of the broad line is due to the proximity of the broad line region to the central black hole, where gas motions are very rapid. The narrow line region contains lower density gas and is farther from the central black hole. So I'll show you the lines again. Actually, let me do this. Let me put that down right here. I know you're seeing this kind of upside down, but wait, let me go like this. Here, that'll be better. That will be better. See how the whey protein container is actually playing a big role in this live, because it makes me be able to put the phone down on top of it at a very correct height. So there we go. You can look at that spectrum. In fact, look at that spectrum. I'll be right back because I need to check on the cat genie. Okay, that is happening. I think Baji turned on the cat genie because it was not in the manual-ish mode anymore. The manual mode of where it normally where it is normally. Interesting enough of a phenomena with that. Okay, so here are the lines, the emission lines that we are talking about. So over here, these two lines are at the wavelength of 4959 angstroms and 5007 angstroms. So they're kind of close together. And more over here is where we have the 6563 angstrom line. So the emission lines from forbidden transitions, such as the O3 lines, these are relatively narrow, whereas the emission lines over here, see, this one's pretty wide right here. These are the ones that's from the H alpha line. That's the H alpha line, which actually, these are the emission lines from permitted transitions, such as the H alpha line, which have two components, such as the 6563 angstrom, which have the two components. So that's what this is saying. One component of a Seifert 1 permitted line is narrow, but the other is very broad, with a Doppler width of around 5,000 kilometers per second. The broad and narrow emission lines arise in two different regions of the AGN. The broad line region contains relatively dense gas, so that's where the broad comes from, in which the forbidden lines are collisionally suppressed. The width of the broad line is due to the proximity of the broad line region to the central black hole, where gas motions are very rapid. The narrow line region contains lower density gas and is farther from the central black hole. This is the Seifert 2. All the emission lines, both forbidden and permitted, are narrow here. These are narrow. This one was the broad one we talked about. In at least some cases, a broad line region is present in Seifert 2 galaxies, but is hidden from our direct view by dust. So a broad line region could be hidden as well. And so we just get this narrow stuff. So that was a little bit of a tidbit about the Seifert galaxies and some emission lines. Now we'll talk about quasars. Radio telescopes first surveyed the sky in the mid-20th century. These first surveys showed that the optical counterparts of most radio sources were galaxies. The radio galaxies discussed in this section. In the next section would be the radio galaxies. However, some radio sources did not have obvious counterparts. So here is, by the way, the spectrum of a quasar. So this is the spectrum of the quasar 3C273. I'm looking to see if it's showing up on the camera. Yes, it is. So this is spectrum of the quasar 3C273 showing redshifted Balmer lines. And this is intensity on the y-axis, and this is angstroms again. So you can see lots of things happening here. So there's, by the way, here's that H alpha line, which was sort of at 6563 angstroms in the previous example. And here's a bunch of other H lines as well. So some radio sources did not have obvious counterparts. Ambiguity arose because of the poor angular resolution of single dish radio telescopes. So some of the issues are with our observation tools, but once better radio positions were obtained, it was found that the radio sources were associated with blue star-like objects. this was unusual. Stars are not generally strong radio sources. It seemed clear that they weren't stars, so their star-like appearance led to the name quasi-stellar radio source, which was later contracted to quasar. So this quasar name comes from the fact, comes from this quasi-stellar. So we thought they were stars, but kind of like quasi-stars, quasi-stars, and then we call them quasars. Quasi-stars, quasar. That's the naming. So this is oh, we have we have a picture. I'll show this to you in just a second. But we will look at the quasar 3C273. You see the spectrum of this here as well, and we have the picture of the quasar as well. But it's mostly a dot. So this spectrum is probably more informative right here. And by the way, some people I think in the past have asked how we understand things about faraway distant objects, and in this case it's a quasar. Well, this type of spectrum is extremely important in understanding what is happening in distant faraway objects, or sometimes these objects turn out to be galaxies in this case. So stars are not generally strong radio sources, so we were a little bit confused about what we were seeing. So it seemed like, okay, they were not stars, but they had some star-like appearances. And so we know that active galaxies have this sort of like activity happening, which is producing most of the luminosity. So that sort of thing can kind of make us think that we have found a star, but then at the same time, when the emission is so bright in radio, that makes us a little bit confused as to what it is that is happening. So seemed like they were not stars, so their star-like appearance led to the name quasi-stellar radio source, which was later contracted to quasar. So note how the quasar, when we look at the picture, we will see that the quasar more strongly resembles the stars in the field of view than the two fuzzy extended galaxies at the left of the figure. So here is a couple of galaxies, NGC 4536 and NGC 4527, and then we have the quasar over here, 3C273, and see how the galaxies have, of course, this extended kind of shape, a spiral shape in this case. This case right here. This one looks to me like sort of a spiral as well, actually. But maybe that's an elliptical, or no, actually that looks pretty spiral to me, like maybe sort of an edge-on spiral. I'm not exactly sure. I have to look up exactly what that is classified as, but this looks very spirally. And then here we have a bunch of other objects in the sky, and then the 3C273 quasar, for which you can look at the spectrum right here. And thank you for liking the live, by the way. Thank you so much. Oh, hi, Sundar. Hello, how are you? We're doing an early live today because I am busy later tonight. So I'll let you keep looking at this as I keep talking here. So the quasar more strongly resembles, as you saw, the stars in the field of view than the two fuzzy extended galaxies at the left of the figure that we looked at. So when the spectra of these quasi-stellar radio sources were obtained, things became more unusual still. The spectra contained strong, broad emission lines that didn't correspond to any known element. The breakthrough to understanding came in 1963 when Martin Schmidt had a eureka moment while looking at the spectrum of 3C273, and he realized that the emission lines in the spectrum were Balmer lines with a redshift of Z equal to 0.158. So not a very high Z, but whatever. That's the redshift. No one had been expecting such a, oh gosh, wait a minute. Oh. So that was considered a high redshift. I was about to say that doesn't sound very high, but maybe it is. No one had been expecting such a high redshift. It corresponds to a radial velocity. Oh, because they were thinking it's they were thinking it's a star. So no one had been expecting such a high redshift. It corresponds to a radial velocity of around 47,000 kilometers per second and a distance of 680 megaparsecs. So people were probably thinking that this is like a star and kind of expecting it to be a bit closer. The large distance was itself impressive at the time, but hardly unprecedented. Clusters of galaxies at redshifts as large as zero point 0.2. So, see, these redshifts don't sound very high in terms of the cosmology conversations we've had, but I guess for the purposes of when they observed it, they might not have realized that it was kind of farther away than they thought. However, what was extraordinary was the luminosity implied by the large distance. So, if you sort of conclude that you are at a large distance away, then you now have to deal with the fact that the luminosity is very high. So then what is it? That's the issue. So if you thought it was a star, it actually turned out to be kind of farther away. Now you also kind of have to deal with the fact that it has a higher luminosity. A quasar is an AGN that has a very high luminosity, which is so around 10 to the 38 watts. Again, we've looked at numbers like this, where we spoke about, for example, the gamma ray bursts were significantly higher than this luminosity. But this is a pretty high luminosity in terms of the AGNs. So everything is a little bit, everything is kind of relative. But this is an AGN, which is of course a different kind of phenomena, and it's a whole, it's a galaxy that's kind of powered by this AGN. So this 10 to the 38 watts number is pretty high for that. So the most luminous quasars have around a luminosity of around 10 to the 41 watts, which is around 3 times 10 to the 14 solar luminosity. The reason why they look quasi-stellar is that quasars are much more luminous than the sum of all the stars in the galaxies that contain them. Thus, the quasars usually appear like unresolved points of light, just like stars. So that's what's really happening here. They look like they might be kind of like stars or quasi-stellar because the active galactic nucleus is much, much more luminous. It's kind of rivaling the luminosity of the sum of all the stars in the galaxy. And so they look like unresolved points of light, just like stars, whereas actually the whole thing is a galaxy. And we just think that it looks like a star. So this is the case, by the way, with a lot of the things that we're looking at in the night sky. Many of them are actually galaxies. Of course, some will look like a galaxy if you use a telescope. Like, in this image, we saw 2 more extended bodies, which are really galaxies. But even if you looked really hard, a quasar might look more like a star or quasi-stellar than a galaxy. So initially, it was difficult to believe that the highest and lowest luminosity AGNs. So apparently, wow. So the highest and lowest luminosity AGNs represent the same phenomena. So that's another thing, is that there is some diversity in the luminosity, but the same phenomenon of the active galactic nucleus is what's happening. So the energy requirements needed to explain quasars, the energy requirements needed to explain quasars were so radical. Basically, this was very confusing back then. They thought these things were stars. Turns out they're galaxies. Turns out they're kind of far. Turns out the luminosity is very high, but also has quite a bit of variability. And even the variability, it's all coming from the same sort of phenomena. So that variability is also important. the low luminosity, the high luminosity, the fact that this can be, it's kind of like crazy. So the nice word for that is called active galaxies. So the energy requirements needed to explain quasars were so radical in the 1960s, and a 20-year controversy over the nature of quasars ensued. So people probably fought about this quite a bit. They were wondering what these things are. Are they high luminosity versions of Seyfert galaxies at the large distances implied by their redshifts? Or are they low luminosity, nearby objects of some sort, with their large redshifts due to some other effect than the expansion of the universe? For most astronomers, the matter was settled definitively in favor of the former hypothesis in the 1980s, with the detection of stellar absorption features in the faint fuzz surrounding quasars. So because of stellar absorption, thank God, we were like, okay, these are high luminosity versions of the other active galaxies that we kind of know about. That's what they realized. The remarkable properties of quasars soon led to more efficient ways of discovering them. For example, quasars are very blue compared to stars, so searches for objects with ultraviolet excess. So that's what it's called, ultraviolet excess relative to starlight, of course. So starlight will have less of this. Proved to be especially effective. Moreover, it quickly became, so if you're looking for this thing, if you know how to, if you know what you're looking for, then you're going to find more. And they did. So it quickly became apparent that there was an even larger population of objects that had the optical properties of quasars but were weak or even undetectable emitters at radio wavelengths. So they might be kind of radio quiet, but may have optical properties. So these were the radio quiet sources, which became known as quasi-stellar objects, or simply QSOs. The original radio loud quasars make up only about 5% of the total population of quasars. So at first, when they saw originally the quasars, they thought that they were very radio loud, but then they started to find more and more of the, it's almost like you have to find the thing, more examples of the thing before you can kind of really classify it, right? So turns out that the radio quiet sources that they found that basically had other of the same features were considered quasi-stellar objects or quasars. Intensive searches for quasars turned up yet another variant of the AGN theme, objects that are known as BL-LAC objects. Thank you for liking the live. Unlike Seyfert galaxies, which are named after their discoverer, BL-LAC objects are named after their archetype, which is the BL Lacertae. I don't know how to say that. Lacertae. The name BL Lacertae is the type of name, 2 letters plus the Latin genitive form of the constellation name that is given to a variable star. So it's kind of like we're coming now from the direction of variable stars in the naming. In fact, BL Lacertae was originally thought to be a variable star within our own galaxy. However, deep exposures reveal, so even better pictures, reveal that BL Lacertae is not a star, but a distant elliptical galaxy. Its redshift is 0.07, puts it at a distance of 300 megaparsecs. The reason why BL Lacertae was originally mistaken for a star was that its unresolved nucleus is brighter than the diffuse fuzz of starlight surrounding it. The nuclei of BL Lac objects are rapidly variable and have a non-thermal spectrum, but do not show any emission lines. Let me show you some more pictures right here. This is gonna be so by the way, as I tell you the rest of the story here, you can look at these. So these are NGC 4051 at a redshift of 0.002, MRK 335 at a redshift of 0.0256, and then PG 0953 plus 414, which is at a redshift of 0.234. And so these 3 AGNs have comparable apparent brightness, but each step from here to here to here represents an increase in distance of about a factor of 10 and an increase in luminosity of about a factor of, well, almost a factor of 100. So closer to less close to least close. Increasing distance, factor of 10, and an increase in luminosity of almost a factor of 100 happening here. Wow. Wow. So yeah, far away, it can definitely look more like a star because of the quasar properties. So the because of no non-thermal spectrum, or the nuclei, or sorry, they do have a non-thermal spectrum. The nuclei is they're very rapidly variable. They have a non-thermal spectrum, but do not show any emission lines. This makes it difficult to determine the distance to a BL-lac object unless you can manage to detect the absorption lines in the fuzz of starlight. Doing so is very difficult for many BL-lac objects since their nuclei are so extraordinarily luminous compared to their stars. It also makes it difficult to determine their morphology. It's conjectured that all BL-lac objects are ellipticals, but no one is totally sure. The flux from a BL-lac object can change significantly from one night to the next. This indicates that the bulk of the luminosity comes from a region less than one light day. So this is all happening within a light day across length, because light years, light days, and light seconds are a length. It's the length of time traveled by light in a year, for a light year in a day, for a light day in a second, for a second. So a light day is around 200 astronomical units across. We are 1 astronomical unit away from the sun. Light takes 8 minutes to travel that distance. When you have a light day, it's more like 200 astronomical units. So so the bulk of the luminosity comes from a region that's less than 1 light day. So that's pretty short in terms of the how much luminosity you're getting. Seyfert galaxies were first noticed because someone looked at images of spiral galaxies and said, wow, those nuclei are really bright. BL-lac objects were first noticed because someone looked at the radio emission and said, wow, that's way too much radio emission for BL-Lacertae to be a star. So it's interesting. It's very interesting how these things were kind of discovered based on expecting one thing and getting something else. The nuclei being really, really bright, and then a quasar being star-like, but then being very, very radio loud. And then they found some radio quiet ones as well. So if they thought that they were stars, and it's it's funny that the radio loud ones led them to discover quasars, but actually many of them can be radio quiet. But we wouldn't have known about this type of category of galaxies if we didn't find these kind of strange things. So that's where we are today. We will continue this discussion. Oh, I see that Stephen was here. Hi, Stephen. Oh my gosh. Okay, I see the comments now. We just want to see, can you explain what NGC stands for? Stephen, are you here? I did not realize that you're here, Stephen. You can look at those in the meantime. I did not realize that you were here, Stephen. You're the only one that cares about the astronomy in this chat at this moment. So I believe that, so Stephen asked about the NGC, and I looked it up because I wasn't super clear what it was myself. It seems to be the new general catalog. So there are different catalogs for the different events that happen in the sky. Sounds like NGC, and please verify this yourself because I'm just kind of looking it up myself here. NGC is New General Catalog, which is an astronomical catalog of deep sky objects. The catalog was compiled in 1888 by Danish astronomer John Louis Emil Dreyer. NGC is a catalog of nebulae, star clusters, and galaxies. So we have actually mentioned a number of these NGC examples of galaxies. So I thought they had something to do with just galaxies, but it turns out it's just a catalog. So, and it's more general than only galaxies. So thank you for asking that question. We may have to run. I need to go to the gym and take a swim. Just ignoring the posts. Yes, I am. Just ignoring the posts. Just came on a few minutes ago. Steven, thank you for being here. What do you mean you're ignoring the posts? You mean the chat messages? Yeah, the chat has been kind of crazy today. I was interrupted a little bit because I have some things going on in the house. Like I had some work happening here. Then I had groceries being delivered and all that stuff. So sorry about the interruptions today during this live, but we did cover active galaxies, AGNs, Seyfert galaxies, and quasars just now. And yeah, tell me how things are going, Stephen. Okay. All right, I will fix their water. Hi, Saji. You know what? Man, I wish to do clips today, or did I? What did I just say? I said I forgot to do clips today. I forgot. I forgot to clip today. Safe travels. Today is a crazy day. I had too much going on today. But I wanted to cover Active Galaxies, and I did. At least I did that. At least I did that. And I still have more things to do. I have the flu, but I have the flu, but I'm staying home safe. Oh gosh. I hope you recover very soon, Stephen. Oh, actually, I need to charge my phone. Hopefully you guys enjoyed that image of the 3 quasars. I need to charge the phone, and I need to run to the gym. Good night all, and we did land on the moon. I know, we did. Stephen, have you been coming to my night lives? They have actually been a lot more kind of better, and the chats have been really good, and there have been a lot of discussion and questions and relevant type of, people who are interested in the topic, lots of questions and things like that. So I think you might, if you missed it, you might have missed it. The last couple of night lives that I did were actually very, very good, with a lot of really good participation. So you might, yeah. I feel like if you want to go back, I know you have the flu, so first of all, take care and have a great, well-rested few days, hopefully. But yeah, once again, these are the 3 AGNs, going from closer to farther away. Closer, less close, least close. But I know this live was a little bit crazy, and apologies about that. I hope that we will see you very soon at more of the night lives. But if you want to go catch up on the last few days of night lives, Stephen, under the live tab on my channel, we had some really, really good discussion spurred by what the audience was asking, actually. So I thought that was great. So if you missed it, would love to see you on those videos, and then you can always leave me a comment with any of your thoughts or questions. Okay. Hope you enjoy it. Hope you enjoy it. This is funny. What I was a little bit surprised by the redshift numbers here, to be honest. And I feel like I was sort of in that cosmology mode. So it's remarkable how redshift, you know, and how things are close or far is quite relative, and it can be, of course, different in astronomy versus cosmology. When we do our cosmology live, I will rehash this with you again. But thank you for being here today, and thank you for supporting the live as usual, and or watching this later on as a video. Thank you so much. Oh, thank you. Okay, thank you, Stephen. Thank you, everybody, for being here. I'll leave you with this awesome picture. Let's look at it quickly. A negative image of the object be a lack. There we go. So we will continue these topics, and thank you so much for being here.